Good morning, friends. I'm Dr. Sudhaker Upadyay. So I first would like to thank the organizer for providing me opportunity to present my work, Thermodynamics of Regular Black Hole, in the third International Conference on Holography and its applications. So this work is based on the paper published last year with Amit Kumar, Dharamveer Singh, Yerolan, and Vilmira in the European Physics Journal last year. So the plan of my talk is as following. First, I'll introduce the problem and we'll discuss a newly constructed regular black hole solution. And then we study thermodynamics of this newly obtained regular black hole solutions. And further, I'll study stability and the phase transition of this black hole solution. And finally, I conclude my talk. So, starting with the introduction, we'll see that Einstein theory of general relativity is one of the successful theory of theoretical physics, but it fails to explain certain concepts of the universe. So there are concepts like dark matter and dark energy are still needs to be studied because it is not understood well quite well. So to improve the situation of a GR, one needs to modify because it does not explain everything in a correct manner. So there is no complete theory of GR, you see. So in such connection, there is a modification in GR by higher derivative terms is called the Lavlac gravity. And Gauss-Bonnet gravity is one special case of Lavlac gravity, which actually modifies the GR. And the essential aspects of GR is to find the solution of Einstein field equations. So there exist various solutions of the GR. If you see, uh, there are mainly two kinds of solution. One has central singularity separated by boundary at the as the event horizon and is known as singular solution. However, another solution which is not singular at singularity at center is called the regular black hole solution. So, Pagine black hole is considered as the first regular black hole solution constructed in GR, where GR commonly coupled to the nonlinear electrodynamics. And the motivation to consider nonlinear electrodynamics is that linearity of the real electromagnetic field or Maxwell theory breaks at high energy due to interaction with the other physical fields. So the properties of nonlinear electrodynamics can be justified from the gravity perspective as strong vector fields dominate at the center of black hole. So the behavior of charged particles around the black holes may be described by the nonlinear electrodynamics rather than the Maxwell electrodynamics. So we'll start a description of gravity and coupled with nonlinear electrodynamics and the Gauss-Bonnet term. So here you see this is a higher dimensional gravity. So we consider it a five-dimensional, and here it is a Ricci scalar, and this is a cosmological constant term. And this part is a Gauss-Bonnet term, where this alpha is a Gauss-Bonnet coupling constant, and this curly L is basically Lagrangian density corresponding to the nonlinear electrodynamics. So the expression for this Lagrangian density for a Gauss-Bonnet term is you can see is a quadratic in a Riemann tensor and the square Ricci tensor, and this is a square of a Ricci scalar. So, this Lagrangian density corresponding to the nonlinear electrodynamics. can be given by this legendary transformation, where this P is a scalar invariant of the Flebinsky tensor P mu nu, and this H is a structure function. And this P mu nu, which is a Flebinsky tensor, is related to the field strength tensor with this expression. So this P mu nu is a basically function of a vector potential A. So if you consider this action describing gravity, so what will be the equations of motion? We'll see here. So by extremizing the action, the above action, with respect to the metric tensor G mu nu, we'll find the equation of motion or Einstein equation of motion with this expression, where this usual ZR term and this is the cosmological term, and where this H mu nu, which is a Planck-Gauss tensor, is a contribution due to the Gauss-Bonnet term, because you can see there is a Gauss-Bonnet coupling constant in the front of these terms. And this right-hand side is basically electromagnetic tensor term, and this is due to the nonlinear electrodynamics, where this H, the explicit form, this structure function, we'll consider later in the next slide. And you can see here that this is basically equation of motion corresponding to the nonlinear field, this A mu nu, which is a vector field. So we'll find the explicit expression of this H, what we have considered. So here we have considered the expression for a structure function. You can see this is a linear, this is non-linear, and the choice of this expression is done by keeping in mind that it goes well over the Maxwell electrodynamics for the weak field limit, and this satisfies the weak energy condition as well when requires. Okay, so with these conditions, this can be considered, and where you can see this S is nothing but this is the free parameter, which is you can see a fraction of the electric charge E over 2 of M. This is the ADM mass will be related to the black hole mass. And here you can see if you consider this structure function, if you calculate the electromagnetic uh, tensor, uh, so as energy momentum tensor, if you calculate, so the non-zero component will be like this. These two are the non-zero component, and rest are zero component. So with this energy momentum tensor, if you put this uh, here in the Einstein equation, and if you solve, then what you find, suppose you are writing the general metric for five-dimensional gravity like this. So this is the spherical symmetric solution, where this FR for our case is calculated by this. So here you can see there are two branches, one for positive and one for negative. So we can see this positive branch gives the instability. So this is not of the much physical interest. So we keep this negative sign for my further investigations. So here you see this horizon condition. If you put this on horizon condition, there is two possible routes, namely R minus and R plus, that correspond to the Cauchy and event horizon. So if you plot the metric function with respect to horizon radius, you can see this is the plot. Here you can see that the numerical solutions are suggesting that there exists non-zero Gauss-Bonnet parameter alpha, and the charge E for different values of this alpha and charge. You can see this FR is minimum, and the size of black hole increases with increasing the value of charge. If you see the charge is increasing, the black hole horizon increases, and also as long as the Gauss-Bonnet coupling parameter increases, also the black hole horizon increases. So if you calculate the curvature in the limit r tending to 0, you will find the non-zero value for scalar tensor, and this is a square of the Ricci tensor, and this is basically Crestman scalar. So here you see for non-zero values of GB parameter, this is a non-zero values. So this suggests that our black hole solution is not singular. Okay, so this suggests that this is a regular solution because of non-zero value when r tending to 0 of these Ricci scalars. So you can calculate the thermodynamical properties just simply putting the horizon condition. So here you see if we calculate the mass of black hole in the horizon condition, this is of this kind, which depends on the nonlinear charge and the Gauss-Bonnet parameter. And if you calculate the Hawking temperature using this expression, usual standard relation, you will find the temperature also, which is more general than this Bardeen black hole. Here you see that when you put this equal to 0 limit, you will get the temperature for GB black hole, Gauss-Bonnet black hole. However, if you put this GB parameter equal to 0, you will get a Bardeen temperature, Hawking temperature. And if you put both this charge, nonlinear charge, and the Gauss-Bonnet parameter 0, you will get Schwarzschild-Tangerlini black hole temperature. So if you calculate the wall entropy, we'll find this. Here you can see that this is not this entropy does not follow the standard area law because of there is two extra terms here and this non-zero term. And you can see in the absence of charge, this entropy will correspond to the entropy of the GB black hole. And since this entropy of the regular black hole does not obey the area law, so this is because the energy momentum tensor already has the mass term. So uh, this corresponds to that your entropy does not follow the area law and also will not follow the first law of thermodynamics, which is required for black hole mechanics. So to improve this solution, this is the case for regular black hole solution where this does not follow the standard first law of thermodynamics. So Ma and Zhao proposed a corrected form of first law of thermodynamics for regular black holes by introducing an extra factor in front of the mass term. So you can see this extra factor is has this certain relation, and for our case, if we calculate, we'll find this expression. So with this expression, if you put here in the uh, first law of thermodynamics relation, you will see that entropy will follow the area law. And now what we do, we calculate the stability. So stability, you can see, can be checked by calculating the specific heat or Gibbs free energy. So here we see that a black hole remains stable for positive heat capacity or negative Gibbs free energy. And the black hole will be in the unstable state when your specific heat is negative or Gibbs free energy is positive. So if you calculate the heat capacity for the Bardeen black hole in the Gauss-Bonnet gravity, the expression we will find is this. It is a complicated expression you cannot understand by this expression, where you can see there are new parameters beta, beta 1, and beta 2, which is not introduced in the theory, but this is a function of nothing but this is a function of horizon radius and the Gauss-Bonnet parameter. So here, this is r square 4 alpha. Here, this is r square minus 4 alpha, this beta 1, and beta 2 is nothing but this r square plus 6 alpha, and this beta 2 is nothing but r square plus 8 alpha. So, this is the specific heat. If you plot this with the horizon radius, what we will get this kind of graph. So, here you see that there is a singularity at this point and at this point. So this black hole we can see has a phase transition twice. Okay, at this point and this point. So firstly, it is you can say smaller. This is a positive quantity, so this is in this region, black hole is stable, and here you can see this is a negative heat capacity. It means in this region it is unstable. So there is a first phase transition where small black hole goes from stable region to unstable region, and further for the second case, it will go for the smaller black hole for the unstable region to stable region. Okay, so the radii are increases with this alpha and e. So here you can see there if you increase a parameter alpha, so horizon radius increases, and also with this charge increases. So from red to green, if you see red to green, also with charge increases, your horizon radius increases. So further, if you calculate Gibbs energy, you will find this expression, and we find that at critical temperature, this expression vanishes. So vanishing Gibbs free energy will give you a critical temperature, which is found like this. Okay, so in general, black hole with the negative values uh, uh, of Gibbs free energy are a stable black hole, and Gibbs free energy with positive value is a unstable black hole. So this is finding. So I do not have much time. So I'll stop here by concluding that we have calculated the Bardeen black hole in the Gauss-Bonnet gravity, which is characterized by nonlinear electrodynamics, and we have calculated the thermodynamics. So we find that a regular black hole does not follow the standard first law of thermodynamics. Rather, it follows the modified first law of thermodynamics, and we have studied the stability, and we find that there exists a double phase transition. Okay, so thank you very much for your kind attention. Thank you.